Hello everyone, I am Pawan and I am a noise and vibration consultant. Today, topic is basically looking at NVH from the electric vehicle perspective. So, how the NVH area is going to change and what are the different things that we need to look at when it comes to the electric vehicles. I've done my PhD in noise and vibrations from the University of Massachusetts uh, way back in 2010. After that, I have been working with several automotive companies to take care of basically the NVH issues. Now, the latest topic is electric vehicle powertrain related to the NVH area. So today, what we're going to do is basically look at all the different uh, important aspects of NVH field in the electric vehicles. So, just to give you a very brief idea of how the whole presentation is going to go and the whole course is going to be laid out. Before jumping on to the contents of the course, I just want to give you a perspective of how the noise, acoustic noise, and structural vibrations they occur, especially in case of electric vehicles. So, like I said, we are going to look at the electric vehicles through this course, and EVs or any non-emission vehicle is going to be the future for us everywhere around the globe. And so, basic question is how is the noise generated in an electric motor? If you look at an electric motor, you will see that you know whatever type of electric motor you have, it could be an induction motor, it could be a synchronous motor like a PMSM, it could be a IPMSM, it could be a SPMSM like interior magnets, surface magnets type of PMSM motor. So whatever electric motor you have, in case of EVs, definitely there will be some kind of AC drive that will drive that motor, and most probably you will have a PWM type of drive. So PWM stands for pulse width modulated drive. So this pulse width modulated inverter basically converts the DC to AC voltage. So it converts from DC to AC, and there is a very specific process that is followed, which we'll be discussing through this course on how the DC is converted to AC. Using this, once the signal is converted to the AC, then that can be fed to the motor to drive it, and the motor will then drive all the components of your vehicle. Those will definitely have some kind of vibrations. So these are called the structural vibrations, which will then be converted to noise depending on the frequency of those vibrations. Also, there will be some frictional forces and basically coming from the ground like suspension and all. So these are different types of noise that could be generated from a motor in case of EVs. So same thing I've just outlined over here with some plots given, like the voltage input and then how the vibrations can be measured, how the acoustic noise is generated through this. There are so many aspects that we need to understand over here. So for example, when you have this motor, there will be electromagnetic noise that is going to be produced. So this electromagnetic noise uh, will uh, will impart itself on the modal resonances of your vehicle, of the motor, and once the resonances are excited, you will get lot of vibrations. So how we can reduce those, all the different strategies we're going to discuss through this course. If you notice over here, we are mostly looking at This is like FPWM, which is 4 kilohertz. So this is the inverter switching frequency. So we discussed briefly about the PWM, that is pulse width modulated inverter switching process that happens. So in this case, it's a 4 kilohertz uh, wave, and then you have got these side bands of 25 hertz on the spectra. So there are three types of noises that you can divide the entire spectrum into. One is the mechanical one. So this constitutes of the bearing noise, for example. Okay. Then there is aerodynamic noise. So this could be, tire noise, or it could be wind noise. Okay. And then you have got the electromagnetic noise. So electromagnetic noise is the motor noise. So the one that we just discussed. At low speed, you will mostly find that there's not much of the noise that is there in the EVs. So this could be one of the reasons that people feel that there's not much of an NVH perspective in the EVs, or there's not much of work for the NVH people in the EVs. However, as the speed increases, you will see that at some speed, uh, the electromagnetic noise is much higher as compared to the aerodynamic noise or the mechanical noise. So when it comes to the mechanical noise or aerodynamic noise, it's very simple. It's dependent on the speed. So as the speed increases, you will definitely have a higher amount of mechanical noise, as well as you will have a higher wind noise or aerodynamic noise. But when it comes to the electromagnetic noise, that is the motor noise, like we discussed, what's going to happen is at certain speed you're going to have a very tonal type of noise uh, which is generated through the motor, and this will be at the switching frequency of the PWM inverter. Okay, and this switching frequency will be at at a different speed. It's not a very low speed or a high speed. However, what you will see is that a very distinct tone will be heard, and this distinct tone is a bit annoying. So, if everything else is quiet, you will definitely feel that, okay, you're hearing something for a longer duration of time continuously, and all the energy is concentrated in that frequency band. So that kind of raises the annoyance coefficient. So that's why it's very, very important to understand how the electromagnetic noise is produced, how the motor noise is produced, and how we can reduce it. So the contents of this presentation are taken basically from a lot of different areas and books, papers, uh, online websites, and a lot of reading that I have done before this. So I've used a lot of material from SAE International. Then there's this company called EOMIS. They do a lot of stuff related to the EV NVH area, and I've used some of the concepts from their material. Then there is also this uh, set of journal papers or articles that are produced by Dr. David Lindstrom. So we are going to discuss a few of those from them. And then there will be mechanical design of electrical motors, as well as a few books that I have outlined over here. So you might want to check out these once this short presentation is done. So what happens when you convert when you are moving from an IC engine to an electric vehicle from the NVH perspective we are talking about here. So what do we really need to do as an NVH engineer or in the NVH field? What's going to be different when it comes to the electric vehicles or hybrid electric vehicles? The future is going to be non-emission type of vehicles. It could be any EV, it could be a fuel cell type of vehicle, it could be a hydrogen vehicle, it could be a hybrid electric vehicle, but there's definitely going to be some kind of motor or some kind of prime mover that is going to be involved, which is other than the IC engines. Okay. So what happens when it comes to the engine is engine noise is going to be very prominent. Okay, so the engine noise, what it does is, like we just saw, it kind of masks all the other noises. Okay, so very important concept, that masking of the noise happens when it comes to the engine. Okay, so so the engine kind of, especially at the lower speed, it doesn't allow the other noises to be heard by us. So for that, it's a kind of a good thing for us, because then engine noise is definitely going to be higher than, let's say, the tire noise or wind noise or any other accessory noise. Okay, so this is called as the IC engine masking effect. So it doesn't allow us to hear the aerodynamic or the accessory noise. Okay, or even tire noise for that matter. So this happens in case of IC engines, but when it comes to the electric vehicle or hybrid electric vehicles, or any other vehicle other than the IC engine, you will see that definitely other noises you're going to hear. So that's the task of an NVH engineer in this case, where you need to design, or you need to take care of other noises. So it's not that these noises were not present previously in IC engine. They were present, but they were not in the audible range. Or even if they were in the audible range, they were being masked by the IC engine. So, this is something that will need to be looked at into greater detail, and then how we can reduce that noise. Those are very, very important things. At high speed, it's a totally different ball game. So what happens at high speed is that you'll have the engine noise, you'll have the tire noise, you'll have the aerodynamic noise when it comes to the IC engine. Whereas for the electric vehicle, you will have motor noise, you will have tire noise, and then you will have the aerodynamic noise. So so the motor noise is something which will be very, very prominent when it comes to the electric vehicle. And there are different parameters which we'll be looking through in this presentation, which will need to be understood and evaluated when it comes to the EVs. So for example, you will need to look at the quality of the noise that is coming through the motor. So for example, it could be the loudness, the sharpness, or the roughness of the noise. Then we need to look at the prominence ratio, the tone to noise ratio, the articulation index of the noise. So all these things we're going to discuss in much greater detail in the coming few slides. So this is the difference when it comes to the type of noise that is emitted from an IC engine and from an electric vehicle. So what's the challenge? The challenge here is that there is no IC engine, there will be an electric motor, and so the motor noise, how it travels to the target, that is the inside of the cabin, that is something that is going to be challenging to understand its path, so that if we can reduce the noise at the source or in its path or somewhere, we can arrest the noise so that it doesn't travel to the all the way to the inside the cabin. So that's something that's going to be the challenge for us. Then basically, for the electric vehicles, the different areas or the sources of noise, where sources from where the noise is going to come is could be divided into all these six different parts or regions. First is the electric powertrain, so where the electric motor is placed. So in the electric powertrain you will see that there's an electric motor. Now every vehicle has a different type of configuration of the motor. Some vehicles have four motors mounted on at each wheel. Some vehicles have only one motor mounted. So it really depends on the configuration and the construction of the vehicle. However, the electric powertrain certainly is one of the most important one of the most important noise sources that need to be looked at when it comes to the NVH. There are different accessories and components that we'll have to look at when it comes to the NVH, as well as the chassis and the panel vibrations, structural vibrations that come into the picture. Because now remember, there's no IC engine noise, so all these other noises are also very prominent and very important. There is battery charging noise. So battery is another totally different type of area that needs to be focused, discussed, and researched quite a bit. There's a lot of research actually going on in the battery area. So it's a continuously changing. The type of batteries and everything is changing quite a bit. So that needs to be looked at. And then there is aerodynamic noise. So the question is how we separate out the wind noise from the structural noise, or from the other noise. So that's something that we'll have to discuss in much greater detail. Okay, so mostly what we are going to concentrate on is electric powertrain noise. So we discussed this very, very briefly, but here's something a good picture of how we're going to go about this. There are different sources of noises when it comes to the electric powertrain. There's a mechanical as well as there is aerodynamic source. So for mechanical, you will see that there's like I said, bearing noise. There will be tire road noise, and then there is the gear whine as well. Okay, so this area of gear whine, so whine noise is also a very important area, and a lot of research is getting done on this. Why? Because again, like I said, this noise is not masked by the IC engine noise now. So because of that, all these different noises are have become very prominent. So this needs to be looked at in much greater detail. Then there is aerodynamic noise, like wind noise is there. Then there is fan blade noise. So again, these needs to be first of all separated from the overall noise, and then how we can reduce this to make a much aerodynamic shape, or all these things need to be looked at for this. Mostly in my presentation, what we're going to look at is the electromagnetic noise. So the electromagnetic noise, like I said, it's going to have two types of noises. One is the slotting noise, and then there will be the switching noise. As compared to the switching, the slotting noise is at a lower frequency. However, the slotting noise has to do with the motor number of poles, number of stator slots, and the construction of the motor, mostly, like the topology and all. So that's what the slotting noise will be. And the switching noise has to do with the inverter. So that's the inverter is the one, like I said, it converts the DC to the AC. So the DC is the battery source that you get the power supply from, and then AC is the motor. So you supply the power from the battery, you use the inverter to convert it to the AC, and then you supply it to the motor so that the motor can operate then. So the whole area of inverter switching is a very, very wide area of research. It's not so simple so as to just convert DC to AC. put in a bunch of rectifiers or a bunch of capacitors and inductors. There's a lot of thought process that goes behind this, and we're going to discuss this in much greater detail in the next coming slides. So motors, there are many different ways to classify the motors, and we are in this presentation, since due to lack of time, we're going to look at only a few of them. Mostly my my presentation will concentrate on the permanent magnet synchronous motor, and we will take a few examples on IPMSM and SPMSM. So you will see that IPMSM is the interior permanent magnet synchronous motor, and then SPMSM is the surface permanent magnet synchronous motor. Why we are going to look at this? Because this is perhaps the most popular electric vehicle motor that is used across the world. And I'm not saying that other motors are not used. Definitely there's induction motor that is used. There are other type of motors, which reluctance motor, that is also used, but the PMSM is the most popular one. And so we are going to take a few examples of how the electromagnetic noise is coming through this PMSM motor. So there are different types of motors. Mostly, if you see, there are two types you can classify. One is the non-synchronous one or asynchronous, and then the synchronous motors. So there's the IM or the induction motor, and then you will see the synchronous motors. Mostly, almost all the motors will have these parts, the coils, so that you can supply current through the motors. And then there will be poles, the stator slots, there will be yoke, there will be a rotor, there will be, you'll find that the air gap is there. So air gap is very important when it comes to the electromagnetic noise. So what's the optimum air gap and how that's going to affect us? So all this, along with that, there will be a control strategy, like we discussed the different PWM strategies we are going to look at. There will be a sign PWM or space vector type of PWM, and then also discontinuous PWM. So, and then comparison of all this we're going to discuss in this presentation. So we discussed this in brief. There will be motor, and there will be slot pole interaction. So what basically happens is, this is the rotor and this is the stator. So this is the stator, for example, and then you will have these slots in the stator. Okay, this is the construction of the motor. So there will be a lot of slots out here. It could be any number of slots. Again, the number is designed by the motor manufacturer. You can specify the number of slots that you want. So for example, you have got 48 slots. Okay, and then this is the rotor. Okay, so rotor will house the magnets. Okay, and then there will be poles. So this is a 4-pole type of motor or 2-pole pair type of motor. And then based on the interaction between the permanent magnets and the stator slots, you will see that there will be some kind of force that is generated in the air gap. So there will be magnetic flux that is generated first, and then because of the magnetic flux, the force will be generated. So the magnetic force in the air gap will be directly proportional to the square of the magnetic flux. So this is the electromagnetic equation that we will be using. From this force, we are going to find how this force affects different areas, different parts of the motor, and what kind of stresses are generated. So we will evaluate the Maxwell stresses in this case. Okay, Maxwell stress tensor, and once we evaluate the Maxwell stress tensor, then we are going to look at what is meant by a wave number. So how these forces incorporate itself as a wave, and how the wave travels across in the air gap, and then once the wave is generated, how it is exciting the the natural frequency or the mode shape of the motor, specifically the stator, and how the noise vibrations is they are getting produced through this. So that's the whole process. And then basically find the SPL, or the noise levels that are generated through this whole process. So that's how the electromagnetic noise is produced, and we will discuss this in much greater detail through this presentation. Now, if you look at the spectrum plot of this, or the Campbell diagram, you will see that typically this is the type of noise that you see will be having two parts. Like I said, there will be slotting noise, okay, and then there will be switching noise. All right. So the slotting noise has to do with the number of poles that you have, okay, and then number of stator slots you have. So based on that, you will have the motor slotting noise. So for example, you will see that the slotting noise over here, these lines of these orders basically represent the slotting noise, okay. So the H24 has to do with mostly the torque ripple, I think. So this is the the torsion, the tangent ripple noise. So and then H48 is because of the uh, pulsating wave number. So that's H48, and then there will be harmonics of those. There will be also switching frequency. So the switching noise is related to the inverter noise. So if you see, this is this is the switching noise, and there will be side bands of those. So this switching is happening at 10 kilohertz in this case. So you will see that the 10 kilohertz there will be a switching noise. So and then if there is interaction between these between these orders, definitely there will be an impact. And if there are any resonances that are getting matched up with these orders, it's even worse in that case. So it's very important to track the different noises that are there. You can see the aerodynamic or the mechanical noise way down at the bottom over here. So this is at a very lower frequency, this region. As you go high up in the frequency, there will be motor noise. Previously, when there was like IC engines, or at that time, you probably didn't have this kind of noises. But now, because of the electric vehicle, the problem is not at the lower speed or at the lower frequency. The issue comes when it is the higher frequency or the higher speed. Okay. There are many different ways to look at the noise, and we will discuss this again as to how you can understand the concept of wave number, electromagnetic forces, and then associated frequencies. What are the sensitive frequencies? We can also use the ODS approach. So this is the ODS of the stator that is shown. So how this ODS is affected at, let's say, the wave number R equals to 4. What different type of forces are generated in the air gap of the motor, and how they are going to produce the noise. So all these things we will be discussing in much greater detail. How you can design for electric vehicles. So what are the different types of sound design related principles that you need to employ? So those are some of the things that will need to be looked at. Okay, so we discussed this very briefly, that electromagnetic noise is tonal in nature. So the type of indicators or psychoacoustic indicators that we need to look at are the TNR, that is tone to noise ratio, and then there is the prominence ratio. These are the two very most popularly used indicators. Noise is definitely shifted to higher frequencies when it comes to the electric motors. There is humming noise is mostly for the lower frequencies. For the higher frequencies, you will hear the whining noise. Uh, so these are the different orders, the whines that you can see over here. And then strong tonal content of the pole or slot effect. So slotting and the switching effect. So these are the two effects that you will see when it comes to the electric motor. So I think we will break here and then we'll come back later.